One of my colleagues at Input Output bought some ADA for his nephews and nieces. And of course, I don't know any details about that. But just imagine you want to make a gift of ADA to a child. So you want the child to own the ADA, but you only want the child to have access to the ADA when he or she turns 18 or 21 or whatever. And using Plutus, this is very easy to implement a scheme like that, a vesting scheme like that. So I copied the isData contract and into a new module that I called vesting. And as our first example of a validator that actually uses the context, I want to try to implement this vesting idea. So you put money into a script and only the dedicated person can retrieve it, but only once a certain deadline has been reached. So the first step is to think about the types of datum and redeemer. And it makes sense to have the datum contain exactly those two pieces of information, the beneficiary and the deadline. So let's do what we did at the end of last lecture, use a custom type for the datum. I call it vesting datum. It's a simple record type with these two fields, beneficiary and deadline. And what should the data types be? Well, the beneficiary will be identified by his or her public key, or rather public key hash, or to be even more precise, payment public key hash. So that will be the hash of his public payment key. And the deadline, as we saw before, Plutus uses real-time, POSIX time. So this is the datum. And we can derive a show instance, which may be useful for debugging, so that we can display values of this type in the console. And as I also explained last time, we don't have to write to data or from data instances by hand. We can use template Haskell with this unstable make is data. Although in production, we would probably not use the unstable, but the stable version. But for simplicity, we can just do it like this. Now the interesting part is the validator function. And as we know, it takes the datum, the redeemer, the context, and returns a bool if we use typed Plutus, which we want to do. So we just talked about the datum type. We use our custom vesting datum for that. So what about the redeemer? So the question is, does the beneficiary need any additional information when he wants to redeem the gift, the deposited money? And in this case, I think we don't need any additional information. So all the beneficiary has to do is, once the deadline has been reached, just try to unlock the UTXO sitting at the vesting script address. So there is no additional information needed. As long as the beneficiary signs the transaction and as long as the deadline has been reached, the funds should be his and should be possible for him to use an output sitting at this vesting address as an input for his transaction and then do with it whatever he or she wants. Which means, so the first argument, the datum, must be of type vesting datum, and the second argument, the redeemer, we don't need any additional information, so we can just use the unit type. And the third argument is of type script context. And we can give names, so we call the datum dat. The redeemer will always be unit because that's the only value of type unit. And this time we actually have to look at the context, so we can't just use an underscore as we did in our previous examples. So we give the context a name as well. We call it CTX. Okay, and under which conditions should it be possible to unlock a UTXO sitting at this address? Well, as I said before, the transaction that unlocks must be signed by the beneficiary and the deadline must have been reached. So I'm using this trace if false again to, if something goes wrong, to give some debug information or tracing information about the cause of the failure. So this is the first condition. We want to check that the beneficiary signed. So we just give this debug information in case something went wrong. This condition was not satisfied, beneficiary signature missing, and then delegate the actual logic to a helper function signed by beneficiary. And additionally, we want that the deadline has been reached. So we will define a second helper function, deadline reached. And if it hasn't been reached, we give an appropriate message, deadline not reached. So let's look at these helper functions. They are refreshingly short. So first we need this txinfo field of the script context. And we need that more than once, so I extracted that. So I define that first here. So info is just the txinfo field of the script context. And now we have to implement these two conditions, signed by beneficiary, deadline reached. So signed by beneficiary, there is actually a helper function called txSignedBy that takes a txinfo, which we have defined here, and it takes a public key hash. And the meaning obviously is that this is true if and only if the transaction has been signed by the owner of this public key hash. That's the second argument. We do have the required signature, the public key hash, in the form of the beneficiary of the datum. So we just grab that, so this field. So now we have this payment pub key hash of the beneficiary. Unfortunately, the txSignedBy doesn't expect a payment pub key hash, but just a pub key hash. But if we look at the definition of payment pub key hash, then we see it's simply a new type wrapper around a pub key hash. So this is just for type safety, that we don't confuse different types of pub key hashes, but the underlying data representation is actually the same. It's just a pub key hash, which means that by applying unpayment pub key hash to our payment pub key hash, we get to the underlying pub key hash. So this. So we have the datum, the beneficiary gives us this first field, type payment pub key hash. Then by applying unpayment pub key hash, we get a pub key hash, and that we can pass as second argument to the txSignedBy function. And that's exactly what we want. Now the more interesting condition is the second one, deadline reached. If we look at this crude diagram, so this is time, and let's say the deadline is here. And let's consider a transaction with, let's first say, this validity interval. So recall what that means. Before the validator script is run, other checks are made, including the time check. So the node checks whether the current time falls into the valid range of the transaction. And only then is the validator run. So we know now that we are in the validator, the current time lies somewhere in the validity interval. But if this here, the first one, would be the validity interval, then the current time could be, for example, here, which would be fine. It would be after the deadline. But it could also be here, which would not be fine. It would be before the deadline. So this validity interval is no good for us. We mustn't declare the transaction to be valid if this is the validity interval. This, on the other hand, is fine. We still don't know where the current time exactly is. It can be anywhere in this interval, but no matter where it is, it's after the deadline. So we must check that we have this situation, that the whole interval is to the right of the deadline. And one way to do this is to use this contains function that we played with earlier, and look at this interval, the half open interval that starts at the deadline and stretches into infinity. And if this interval contains the validity interval of the transaction, then we are good. Then we know no matter where the current time is, it will be after the deadline. So we know the deadline is the second field from our datum, which we can get with the deadline accessor. So this is now the deadline. And we have the info valid range that we discussed earlier from the transaction that we get from the txinfo field. And as long as the current time interval is contained in this one, we can be sure that no matter what the actual current time is, it will definitely be after the deadline, and that's what we want. So this is a way to define this deadline reached condition, and we have the signed by beneficiary, and the combination of the two, the logical AND, gives us the logic we want. So a UTXO sitting at this vesting address can only be unlocked by a transaction that has been signed by the beneficiary and where the deadline has been reached. As always, the validator is the heart of the Plutus smart contract that contains the actual business logic. But in addition to that, as we have learned last week, we need some boilerplate. So as I explained when I talked about typed Plutus contracts, we need this dummy type. I, in this case, called it vesting, where we encode the types of the datum and the redeemer. So in our case, vesting, datum, and unit. And then, just following the same schema that we introduced last week, we can compile our Haskell code to an actual Plutus validator, a typed validator, like this, following the same process that we learned last time. And once we have that, we can get the untapped validator and the validator hash and the address, the actual address corresponding to this script, to this validator, as last week. And I should also mention that at the top of the module, I added some additional GHT extensions like derive any class and derive generic, and also added some imports like to JSON, from JSON, generic, and so on. So let's briefly look at the off-chain part. So this type here, vesting schema, defines the endpoints that we want to expose to the user. And as before in our silly example from last week, we call them give and grab. So give is for the person that wants to set up this vesting contract, and then grab for the beneficiary to collect. So what parameters do we need? For give, I mean, what this endpoint will do is it will create a UTXO at the vesting address with the specified amount and the correct datum. And if you recall, our vesting datum contains the beneficiary and the deadline. So this give endpoint must in particular know those, the beneficiary and the deadline. So this is here. And we also, of course, have to specify how much money we want to put at this UTXO. Therefore, I need a third field, the amount. The grab endpoint, on the other hand, doesn't need any parameters because the beneficiary will just look for UTXOs sitting at the vesting address and then can check whether he is the beneficiary and whether the deadline has already passed, and can then pick those UTXOs and consume them. And we know from the way that we wrote the validator that that will then succeed and no additional information has to be supplied. Let's briefly look at the endpoints. First at give. So it takes the give parameters. And first I compute the datum I want to use. So recall I need the beneficiary and the deadline, and I can get those simply from reading it from the give parameters. Now for the transaction, I need as constraint that I want to create a transaction that has an output at the script address. So I use this must pay to the script with the datum I just defined, and then I must provide the value. So I take the value, the amount from the give parameters, and then use this function here to convert that to a value in Loveless. The rest is as before. I just changed the log message. So I mentioned the amount, the beneficiary, and the deadline. Now for the grab, that's a bit more involved because there can be many UTXOs at this vesting address, and some of them might not be suitable for me, either because I am not the beneficiary or because the deadline has not yet passed. So I grab the current time. I look up my own payment pub key hash. Then I get all the UTXOs sitting at the script address, but of course not all of them may be usable for me, either because I'm not the beneficiary or because the deadline has not yet been reached. So I filter those UTXOs using this isSuitable header function, which is defined down here. And as arguments, it gets my own payment pub key hash and the current time, then the output that I found, the UTXO. And how do I do that? I check the datum of this output, and there are two cases. It can either just be a hash. This is actually the default case, as I mentioned several times before. When you create a transaction that has an output at a script address, you are not required to include the datum, just the datum hash. So there can be outputs there that just contain the hash, not the datum. But in such a case, I have no way to know whether I am the beneficiary and what the deadline is, because I'm not able to compute the actual datum when I just know the hash. So in that case, that's this left case, I can't do anything, so I forget about that UTXO. And if there is an actual datum attached in the transaction, then I try to deserialize that to the right type, our vesting datum type. If that fails, I also drop the UTXO. And if it succeeds, I have to check that I am the beneficiary and that the deadline lies in the past, so that now the current time is after the deadline. So at this point, the UTXOs contain all the UTXOs where I'm the beneficiary and where the deadline has already been reached. And if I'm left with no UTXOs, then I just log a message that there are no available gifts. And if there is at least one, then I try to create a transaction that collects all of them at the same time in one transaction. Actually, in the real world, depending on the setup and the situation, there may be too many UTXOs for me to use them all as inputs to a single transaction, because transactions can only be of a limited size. So to keep it simple, I forget about this case, so I assume that there won't be that many gifts lying around for me, waiting for me to be grabbed. So I just get all the TX out drafts, the references of the UTXOs I want to collect, and I need to create this lookup that contains the UTXOs and also the validator of the script. And then for the constraints of the transaction I want to construct, here I say that I want to spend the script output given by this reference, where I basically loop over all the references I found here. So I loop over all the UTXOs, the suitable ones that I want to collect, and I say that I want to spend each of those. So I just have to give the reference and then the redeemer, and we are always using the unit redeemer. Is a very common case, therefore there's a specific value defined in the Plutus libraries called unit redeemer that gives me this unit redeemer. And now this is something new that we haven't seen before. I can't just create a default transaction with the infinite validity interval, because now I must make sure that I specify in the transaction that it's later than now, later than the current time. Because otherwise validation will fail, because then the validator won't be able to be sure that the deadline has already passed. And then, as before, I use one of these variations of submit transaction where I can specify the lookups and these constraints, and I wait for confirmation and then log a message. And finally, I just bundle up these two endpoints as before, so I give the choice between give and grab and then recurse. So once a give or grab has happened, you can do another give or grab. Let's try this in the playground. First, let's add an additional wallet. And the idea is that wallet 1 makes gifts to wallet 2 and wallet 3, and then wallet 2 and wallet 3 try to grab them. So let's start by defining the skeleton of what I want to do. So wallet 1 starts with a give, And let's wait for one slot. And then there's another GIF. We wait for yet another slot. Normally, it should be possible for wallet 1 to make all the gifts in one slot, so it wouldn't need to wait in between. But the way I defined the contracts, if you recall, after doing GIF or also a grab, I always wait for confirmation of the transaction. Maybe I shouldn't have, but I did. So the endpoint won't be available again until the transaction has been confirmed. So the way I wrote it, we have to wait in between these GIF actions. So let's do the third one. Now let's say the first two gifts are to wallet 2, but with different deadlines. Let's say slot 10 and slot 20. And the last one should be to wallet 3, also with deadline, let's say slot 10. So if wallet 2 and 3 wait until slot 11, they should be able to get the gifts, but not the second one, the one that's only due in slot 20. So let's wait until slot 11, and then both 2 and 3 try to grab. And then let's wait another, I don't know, 5 slots just to be sure. So that's the idea. So now we encounter the first problem. In order to call GIF, we need to get the public key hash or the payment public key hash of the wallets 2 and 3. So how do we find out what those are? If we go to the REPL and import wallet emulator, there's a type wallet defined, and that wraps a wallet ID, and that's some opaque type that we can't directly handle. So actually this wallet type represents real wallets, like a dataless wallet, but also so-called mock wallets that are, for example, used in the playground. So they are both combined under this wallet type. And actually you can get to the mock wallets, the ones in the playground, with a function called known wallet, and it takes an integer. So for example, known wallet 2, known wallet 3. And there's also a function called mock wallet payment pub key hash, which takes a wallet, and if it happens to be a mock wallet, then it returns the payment pub key hash, and if it's a real wallet, a dataless wallet, it would produce an error. So we can get the payment pub key hash of wallets 2 and 3 like this. So that's what we can use. So let's start with wallet 2. So let's say the first 2 gifts I set are to wallet 2, and the third one is to wallet 3. Now the next problem we have is the deadlines, but I already showed you in the first lecture for the auction example how you can convert slots to POSIX time in the playground. So let's find out what slot 10 and 20 are in POSIX time in the playground. So this is the POSIX time corresponding to slot 10, and this is the POSIX time corresponding to slot 20. I wanted to use 10 for the first and the third gift, and 20 for the second one. Now amounts, let's say each gift is 30 ADA. Okay, let's go through it again. The first gift from wallet 1 to wallet 2 with a deadline of slot 10, 30 ADA. Second gift again to wallet 2, but deadline slot 20, 30 ADA. Final gift to wallet 3, deadline slot 10, 30 ADA. Then we wait until slot 11, so that's after the slot 10 deadline, but before the slot 20 deadline. And then wallet 2 and 3 try to grab. So let's see what happens. Okay, looking good. So let's go through the transactions. Slot 0, that's again the Genesis transaction where the 3 wallets get their initial funds of 100 ADA each. Slot 1 is the first gift. So wallet 1 uses as input its 100 ADA, has to pay a fee, gets some change, and 30 ADA end up in the script. Second gift looks very similar. Third gift as well. And now these two both happen in slot 12. So this is incidentally the grab of wallet 3. So the input is this one UTXO, the one gift waiting there for wallet 3. And it ends up belonging to wallet 3. And finally, this should be the one belonging to wallet 2. It also picks up the gift and gets the 30 ADA. But the third gift is still sitting there because we aren't in slot 20 yet. We can try what happens if we wait until slot 20 instead. So let me change this from 11 to 21 and try again. So these should all look exactly the same. This is now wallet 3 that also looks the same. Wallet 3, of course, could also have grabbed at slot 11 already, but it doesn't matter if it waits until slot 21. But here now we see that the way we wrote the grab endpoint actually works. So if there is more than one gift available, all of them are picked up in the same transaction. So now both gifts for wallet 2 are available because we are now in slot 21. So both deadlines have passed, and correctly our off-chain code assembles a transaction that uses both of them as input, and then roughly 60 ADA end up in wallet 2. So everything seems to work as expected. There's one thing I should point out, that I wrote the off-chain code, the wallet code, in a way that only submits the transaction if it can actually grab the UTXO. If you recall, I filtered the UTXO to check that I am the beneficiary and the deadline has passed, which means that we don't really exercise the validator because we only send transactions to the blockchain that then get validated, that will pass validation. That's how we wrote the wallet code. So if you want to actually test the validator, you would have to modify the wallet code. If you like, you can do that as an optional homework. So remove these checks in the wallet and just try to grab everything. And then it should fail if you are not the beneficiary or if the deadline has not yet been reached. And then it should fail during validation, not already just in the wallet, not even submitting the transaction. So you always have to be careful or keep that in mind. Everybody, of course, can write off-chain code. So even though now it works, as long as you use the grab endpoint that I provided, I mean, I wrote it in a way that you never try to claim something that's not for you. But of course, somebody else could write a different piece of off-chain code that doesn't try that. And then if your validator is not correct, if it, for example, forgets to check the beneficiary or the deadline, then something could go horribly wrong. So you must keep that in mind, that only because it works for the endpoints you have provided doesn't mean that somebody else couldn't come up with other endpoints where it doesn't work. Okay, so this is the vesting example, where we made use of the context for the first time and where we made use of this valid time interval in the transaction to implement a deadline.